Now, for the next slide, we have precious Pavel I'm so sorry.
All good.
Pavel Sinelnikov.
You got it.
He is the lead DevRel of ZKM, and today he is going to talk about the entangled rollups. A loud applause to him.
Thank you. Okay. All right. So, hi everyone. Who here is familiar with layer 2s? Most of them. I love it.
And layer 2s or
Just layer 2s in general. Okay. Heard of them. Okay. Well, we're going to take the concept of a layer 2 and we're going to make things a bit more interoperable. So, if I can. Okay, there you go. My name is Pavel. I've been in the crypto ecosystem for about 6 years. I started out in the space doing workshops and presentations, and then I've essentially developed from that to do more of the BD side for Metis. So I like to focus on more of like the practical implementations and processes for the different types of structures. I also did research articles related to different types of bridging techniques. I started my own company based on the concept of programmatic influencer marketing. I also built the governance platform that Metis uses to this day. So essentially, a lot of these structures are based in like the practical setting on like, okay, this technology works, what can we do with it? So what is ZKM? Before I answer the question on what is ZKM, let's answer the question on first, what is settlement? Settlement is finalizing a transaction where the transaction is not able to be reverted. Here we have Kraken. And in Kraken, they have a list of different times to finality, when you can actually withdraw from the network. So we see on different networks, there's different finality requirements. We see on the most recent Ethereum proof of work, which is actually the fork for when ETH 2.0 was live, there was Ethereum proof of work. And over here, we see that Ethereum proof of work has 3 to 4 days of time that it needs to take for finality to occur. Essentially, this means that the Kraken will only accept your deposit after 3 to 4 days on Ethereum proof of work. Whereas on Ethereum, on the Polygon network, it takes roughly 10 minutes. So we see different levels of finality for different blockchains. And we specifically look at exchanges because exchanges deal with the day-to-day monetary aspects. So they don't want to give you money and then potentially for the block to be reverted, and they in fact don't have the money. So this is the main aspect that they're using to process their financial transactions. So universal settlement. The idea of universal settlement is any computation can be executed by one blockchain, and the results of the execution can be resolved to any other blockchain. And that's the idea that we want to go for within ZKM, is that idea of universal settlement. The idea of an entangled rollup is to be able to trustlessly pass messages from one chain to another using ZK proofs. So this is I'll be a complicated diagram for this, but hopefully I can give you a better diagram in the next slide. But as you can see, there's a lot of moving pieces here. But it all comes down to this picture right here. This is just a proof of concept picture, but the idea is still the same. It's to connect different types of incompatible ecosystems using layer 2s as a form of an adapter. And essentially sharing liquidity across all these different ecosystems through these different layer 2s that are all interconnected by these ecosystems. So here's Alice. Alice wants to transfer 100 USDT from Ethereum to Avalanche. She wants to make sure that her transfer is trustless, extensible, and liquidity optimized. More on the liquidity optimized part. And I'll go into like a little bit more detail on what that means. But a bridge is essentially transferring assets from one ecosystem to the other. And we have different types of trust, liquidity, and infrastructure assumptions. So different types of complexities related to all of this. We have one is externally verified bridges. So externally verified bridges are, actually let me just give you an example of these. These are all externally verified bridges. These are bridges that are dependent on a different set of validators. So validators that are all, they have a lower degree of consensus assumptions than the base chain that they are essentially bridging. So different types of these types of bridges exist, and they all basically rely on the security of their validators, or their specific validator network, in order to make these bridge transfers. So externally verified bridges receives the request, achieves consensus, then relays the request. So there's different networks that have this, and most bridges that are used today are externally verified. So essentially they have their own type of consensus mechanism in order to transfer assets. Externally verified bridges themselves have high security assumptions, and they might not have the liquidity to facilitate operations. There are different types of methodologies to this. So if who here has heard of multi-chain or any swap? Okay, a few people, okay. But that would bust. But any swap essentially had the concept of any USDT. And so that's basically a mintable token. For a mintable token, you can mint any corresponding amount of that token, but you might not have enough liquidity for that token to be able to actually use it. So if I mint 100 million any USDT from Ethereum to Avalanche, but there's not enough liquidity on Avalanche in order for me to swap that to real USDT, then the bridge, then it's really hard for me to actually use the bridge, because I'm not getting the asset that I want. I just have the wrapped version of that asset. So can we use a layer 2 for this structure? Now, the layer 2s are essentially what are considered as natively verified bridges. And natively and layer 2s are essentially the ability to take assets from a layer 1 like Ethereum and transfer that to a network like Optimism, Arbitrum, Metis, any type of layer 2 that essentially represents that asset one-to-one on that layer 1. And we call this natively verified because you're essentially dealing with the layer 1 as this true consensus. So you're using the validator set of the layer 1 to achieve that finality. So what does this mean? Well, in order to make any type of transfers from a layer 1 to a layer 2, you need to do that transfer on that layer 1. That transfer has to be validated by the Ethereum validators. And then only after they're validated does the transfer actually progress to the layer 2. Now when you want to transfer it back from the layer 2 to the layer 1, the same process has to occur. You're making a transaction, or the sequencer in this case makes the transaction to layer 1, which then finalizes whatever type of transaction, the withdrawal that you're trying to do. We see a number of different types of natively verified bridges, Arbitrum-based, Optimism, etc. All of which have pretty high TVL that's locked. So I essentially described a little bit about how this works, but we'll just for brevity, we'll take a look at these layer 2s in general. So layer 2s often are thought of that they can only protect against assets on that layer 1 itself. So essentially, I can only use that layer 2 for layer 1, I can use that layer 2 only to that layer 1. I can't use it for connecting different networks. But what we've looked into, and what we're actively doing research in terms of this connectivity between different ecosystems, is that we can actually use layer 2 as a method of transferring different assets via and transferring different assets on different layer 2s on different networks, as you saw in that previous picture, where the layer 2s are connected to different ecosystems and used as more sort of as an adapter. So ZK bridges. The idea of a ZK rollup, there's different types of ZK rollups. There's privacy-oriented ZK rollups like Aztec. And then there's the more of the scalability type of ZK rollups, such as ZK sync or scroll. And how they work is that they take a bundle of transactions, create a proof that proves that the execution did in fact occur, and then puts that execution directly on layer 1. So the entangled rollup, how does this look like? We're taking the architecture where the layer 2 is an adapter, and ZK proofs are the method of communicating. So if we just take a look at what's it called? You take a look at any type of travel adapter that you have, and I'll actually pull out one over here. So you have these adapters, right? These adapters can fit into whatever plugs that there are. So think of layer 2s as a method of, if I have a chain which is the power supply, I can take an adapter, plug it into the chain, and start using that electricity without exposing myself to the risk of electrocution. So then think of it like this. So ZK proofs are the wiring, and the layer 2s are just the adapter that goes in and actually charges your whatever devices that you have. Now, taking a look at liquidity optimization. We have remember that complicated diagram for the entangled rollup? Well, the idea of the universal L2 is essentially an extension of that. It's taking the combination of native verification with shared liquidity. So in this case, 100 USDT deposited on Ethereum, and 100 when the USDT is deposited to Ethereum, and when the USDT is deposited on an Avalanche via different layer 2s that are connected to Avalanche. We can actually have a lot of liquidity that's present within these layer 2s that are all shared across all layer 2s that are connected via this mechanic. I'll show you how that looks like. So, for example, if I'm right now, layer 2s that adopt this type of universal L2 structure, if I send assets to this layer 2, I can use these assets across every single one of these layer 2s. So these are all now active liquidity within all of these layer 2s, that every single layer 2 that connects to the system can share liquidity across each other via these different mechanics, via ZK proofs. And then the settlement occurs directly on each layer 1 where all these transactions are natively verified. So taking a look at just this whole example, right, where Alice was transferring assets from Ethereum to Avalanche. We're taking layer 1 Ethereum. We're depositing 100 USDT. We're taking it to an Ethereum Universal L2. Then what we do, this is where the cool part comes in. We can burn a specific amount of assets on a layer 2. We can burn it to a burn address. So if you're all familiar with 0x0000, that's basically an address where nobody owns the private key to. So you can be guaranteed that that whatever that you're burning is actually not in circulation anymore. Now that it's not in circulation, we can generate a proof of burn, which then mints, it acts as a receipt where I can mint a corresponding amount of that asset on a completely different chain. And this way of generating a proof based on preset conditions allows you to then mint it on a corresponding layer 2. Now, I did mention before about multi-chain, any USDT. Any USDT has to be converted into USDT. In this way, because I'm using the native mint function of these different layer 2s, the USDT or whatever assets that I'm minting is native assets. So these are one-to-one with that token that I want to represent. So essentially, in this way, I am actually getting USDT directly on that network because I'm using the native mint function of that layer 2, which is the official address of whatever the swaps of that network implement. And then, obviously, as the final step, I could withdraw those assets directly on this network. Going back a few slides, you might say, well, why do I need to, what if there's not enough liquidity on these different types of layer ones, right? What if the avalanche doesn't have, X amount of USDT? There's different networks that have various different levels of liquidity. And these are all essentially on L1, on Ethereum. These are billions of dollars locked up in these bridge contracts. So because these assets are represented on a different chain, means that you could still withdraw. You could still use those assets directly on the layer 2. You might not be able to withdraw it to that specific layer 1, like on Avalanche. But you still would be able to withdraw it on a completely different network that does have that liquidity. So the idea is I'm essentially using a representation of that asset without any, I'm essentially using the liquidity from different ecosystems, and I'm using it across different chains. And although it might not be, the liquidity might not be on Solana, it might be on Ethereum, I can take assets that are on the Solana layer 2, transferring them back to the Ethereum layer, universal L2, and then back to Ethereum. So in all cases, I'm still able to redeem all of the assets that I have received on any of these layer 2s to any other L1. And taking the consideration that all of these L1s operate very similarly, all of these L1s are connected by major exchanges, all of these L1s all support USDT, and essentially all of these operate in very similar ways. So taking this type of similar infrastructure, we can essentially create a way that we can optimize liquidity across these various different types of ecosystems. So we got tons of pros. One is trustless. So because I'm depending on ZK proofs as a method of communication, I don't have to depend on an external third party to validate any transactions. So I don't have to depend on an external blockchain to manage these transaction transfers between different blockchains. Next is that it's interoperable. So as you can see, the different types of networks that are supported can be EVM, can be non-EVM, et cetera, et cetera. Then we see that it's liquidity optimized. The assets that I'm depositing on the Ethereum layer 2 and potentially the assets that are available there are available across all of the layer 2s that adopt this type of way of liquidity transference. So essentially, I can use that liquidity across all the layer 2s, across all layer 2s of every ecosystem. So very liquidity optimized. There's no potential dry spots on those layer 2s. And yeah, any bridge funds that enter the network can be used across all networks. And then finally, we have the layer 2s. Layer 2s are known to be scalable, right? I can process way more transactions on that layer 2 than I do on the layer 1. So that itself is also a value proposition. Most of the funds, this is a thesis, most of the funds will be on layer 2s. We see the app chain thesis roll around where different app chains are being created, and as a result of these different app chains, they all have the same problem of not enough liquidity. So we can integrate this within the app chains that are created, and as a result, share liquidity across all of these different app chains, all within the same ecosystem. So liquidity doesn't need to be an issue. And then, I think I mentioned that last point. Different cons related to this. So, one major point. The layer 2 needs to accept ZK proofs as a means to mint. And that's a very dangerous, what's it called? Opens up the risk potential for those assets. We also, taking a look at just this whole structure, if potentially any of these layer 1s, the networks are not sufficiently decentralized that are added, a single vulnerability on these layer 1s can potentially lead to catastrophic levels of what's it called? The backing of assets can potentially be, the assets that are on the layer 2 potentially can't be backed by the layer 1 assets, and that's the worst case scenario. So in this case, any new addition to, any new layer 1 addition risks the assets of all of these layer 2, or all of these layer 2s that are built on top of it. But the same goes for Aave, right? Any asset that goes into Aave potentially has the effect of people coming in and introducing bad liquidity into the system, essentially being able to take those assets and then leverage all of those assets to then compromise the token prices of them. In Curve, recently, well not recently, there was a while ago in Curve, the founder of Curve was actually leveraging Curve and risked being liquidated. And as a result of that liquidation, the price of Curve would have plummeted. And so, as a result, you know, these liquidity risk factors do exist in other protocols. We're just taking this and expanding this to, you know, the aspects of layer 2s. So potentially an Aave style system where we essentially take the security of, instead of assets, we take the security and the risk factors of different chains, and we basically analyze each chain being added to this type of universal L2 structure. And the second point is dry spots, right? If I make a withdrawal to somewhere, right, I'm not guaranteed that those assets will be on that layer 1. As we saw with Avalanche, that Avalanche USDT might not be present. If I'm trying to withdraw, let's say, hundreds of millions of dollars, I might not be able to get those assets to that specific layer 1. But I do know that those assets are likely spread across different L1s. I just have to, you know, essentially within this model, balance out how much assets I want on each individual network. But the idea is that any assets that are leveraged or any assets that are deposited to this network can be used across all these different networks. And so that's where the power comes in, is that it doesn't matter if just Ethereum is providing all the liquidity. We can take in that liquidity on Ethereum across all these different ecosystems. And yeah, I can go on, but I think I'm hitting on the on this. So just going really fast into all of this. We're actively doing research across different types of implementations of this cross-chain bridging and cross-chain messaging aspects. So like, okay, I have to mention like these things. The decentralized relay, you know, how do I propagate messages across different blockchains effectively without a single point of failure? I know like, for example, in the Cosmos ecosystem, certain node operators often depend on like centralized, like a single centralized node for processing different types of transfers. So Cosmos Hub, you know, if that goes down, if the relay network goes down, then I can't send assets directly for this. But that's a common problem across any type of relay type systems. So there's like there's different ways of implementing this, including with like intent-based and all of these other structures. But this is definitely, you know, one of the key research areas where how do we guarantee that my proof will be accepted across different ecosystems without having the client generating all the proofs locally, because that's, you know, for some clients that might not be feasible. VM interoperability, you know, there's still these like little things across these different ecosystems that, you know, how do I securely manage transfers between different types of VMs, right? And how do I do this in a way that's trustless, in a way where prevents the most amount of bugs coming in? You know, is there a layered security mechanism that allows this to work as securely as the base chain? And finality, right? You know, we see that on Ethereum where we have 70 blocks and 14 minutes for finality, but we see on Ethereum Classic it takes roughly 2,800 blocks for 12 hours of finality. So we see like there's different levels of finality, and how do we make sure that we get a unified finality across all the different blockchains that are integrated within these systems? So that's also like a very key method of research. So, all right. within the settlement network. So what we're doing is we want to collect different types of research-based, what's it called? We want to collect different types of research-based implementations of these different types of cross-chain interoperability. So we want to make sure that everything in relation to like categorization of different blockchains, we wanted to categorize different types of implementations of layer 2s. So we want to essentially take a look at how people are processing different types of cross-chain transactions. So if you want to take a look over there, we have our first research group was from the University of Calgary. They did a lot of the initial work for this. So we're definitely, trying to make this a bit more prevalent, seeing different risk factors, different implementations, because most of these bridges, most of these layer 2s often share the same types of infrastructure for this. And yeah, that's everything for the presentation.
Thank you for this awesome presentation. Hope we can unify a little bit because it's a hard thing to do, yeah.
Exactly.
Now we will have Dylan Kawalec with building a Bitcoin layer 2 with ZKM. He's from the Gold Network. Can I take a motivation applause for him?
Jimmy, I sent you the slides. Yeah, I just need to create. I sent you the slides here. Yeah, the first two are the best ways. Like layer 2 is a really big infrastructure. Okay, it's going to be that. Even layer 2, the layer 1, like to make that work. So you need to outsource that to a different layer 2. Or sorry, outsource that to your improvement network person. The idea is that anybody who even if it has these down, you can still with the right SharePoint still generate your Pearson. This one, right? Range. Okay, like you're basically saying, I'm communicating to this blockchain and its assets. Like I'm not passing anything else as it goes out. And in tensor, how does someone help me right now? What's that? How do I do this?
Oh, it connects to a different screen. So this is a different monitor. So you need to.
Okay, cool. All right, hi everybody. My name is Dylan Kawalec, and I'm with the GOAT Network, and I'm their head of developer relations. And right now, I am out here today, really discussing with you the implications of really building a Bitcoin layer 2 using ZKM. This entire event and a lot of the discussions that you're hearing now are about ZKM, and I'm going to tell you a lot of the things that Pavel had just gone over. Actually, what is it like to implement the ZK MIPS, but for a rollup, and what are the problems that we face today, and why was it necessary that we started to build a rollup using it. So if you want to use this link, these are the slides, just in case if you get lost or if there's something you want to look at, just take a screenshot, or that's on the bit.ly there, so in case you want to go back on your own. So Bitcoin development today is basically very expensive, and when you're running a proof right now, hash rate is doubling every 4 years. This is actually a good thing when it comes to computation. If you can assess computation, it means that you can actually assess for cost over time. So because Bitcoin's hash rate technically doubles, what you could say is that because the difficulty target of hash becomes more and more difficult, it also becomes more and more expensive. And so Bitcoin's actually becoming more and more expensive over time. And so miners are actually going to be more and more, let's say, limited as time goes on. And so layer 2 adaptations such as Lightning Network are one of few, and we needed more. And so layer 2 is really just the idea of tapping into the tooling that is available to Bitcoin. But what kind of tooling is available to Bitcoin? Some of them are like BitVM, there's Frost, there's Taproot, so on and so on. We use an amalgamation of BitVM and Taproot, which effectively just means that we write commitments to and from Bitcoin, and we can later verify these using ZKM, which I'll show you. But again, it's a problem because we have very limited development tooling, and so Bitcoin needs new development platforms, and we're all very familiar with why Ethereum has grown to the adaptation today. So maximalism is the second biggest problem. And I'm here to kind of talk about maximalism because, you know, we have the United States elections. We understand that democracy is really just like maxis versus maxis in politics, but in our case, we have maxis versus maxis in crypto. So it's a weird idea to have maximalism of any idea. It's actually an anarchist idea. And anarchy is sort of the true tribulation of the soul of the degen. Like why you become a cryptonaut is because you're there for sovereign data, you're there for privacy, you're there for all these really good principles, but then you also don't understand that the rest of the world doesn't care about your ideas on where Bitcoin goes or where privacy goes, because to the world, it just seems like it's a scam, a lot of criminals use it, and so on. So stop being bullish on tokens and crypto, be bullish on the technology. And Bitcoiners need to be more bullish on ZK and layer 2s because they're they don't trust it. They don't trust it, they don't want to touch it. We've talked to 1,000 of them at this point, and they don't want to get anywhere near an L2. But that's where I'm going to tell them how it works. Because the problem that they don't understand is that there's hardly anybody using Bitcoin. And there's about 219 million holders with a lot of Bitcoin, and then nobody actually generating yield because you need transactions in order to actually generate a yield. Yield doesn't exist without transactions. Like if you don't have transactions, you can't generate any interest. So what's the difference between interest and yield? Interest is when you generate a transaction based on the total lock of some asset. But then the transaction volume on a network is actually rewarding the sequencers, the validators of a network. This is the transaction volume that is then rewarded to the network. That is a yield. The interest that's earned on top of that yield can be yield optimized. But you combine both. But you cannot get a yield optimized strategy without a protocol that is cost efficient as well as optimized for Bitcoin yield. Yield Bitcoin means that you're either centralizing the deposit. 250,000 Bitcoins as of 2024, this year in October, these assets were the only assets. The total supply of DeFi, BTC, whether it was wrapped or these. So there's not enough Bitcoin liquidity, not enough people are using it, and we understand there's a shit ton of it, and then where's all the yield? Where's the yield? Everyone's talking about Babylon, and we got all these things, and yield optimization, yeah, I'm gonna throw names because it doesn't make any sense. You can't make a yield optimized protocol without a cost efficient system. So these were the project ending challenges that we face as a layer 2 for a Bitcoin using this. And so like I said, a cost efficient and fast infrastructure. 2, we needed to decentralize the sequencer instead of having a centralized sequencer. We needed to be able to actually decentralize the sequencer so that there was more than one-to-end honesty assumption for the existential risk factor. Because most L2s have a single bridge. The other thing is that if you commit and you verify validity proofs from Bitcoin, you must have an optimistic challenge protocol. This is yet to be developed. And this is actually going to be the thing that we're working on for the next year. Okay? So the Bitcoin bridge and the GOAT network is the proof that we have GOAT that is locked as the value of Bitcoin on layer 1, and it's minted as gas, and we say it's GOAT BTC, right? The greatest of all time. So we use any VM that a developer would be familiar with so that we can start building PTC applications. So it's basically using Ethereum, and then we can transition on to what other ecosystems, and most of them are EVM, so we're not going to have too many problems there. The solution is and was ZKM for all of this, actually. Enabling even the fast ecosystem access so that we can have types regardless of the data sourced from the chain. So you create a proof is very slow, but once you create a proof, you can enable fast interoperability, or what's known as strong interoperability. You can also do many other things like creating a custom relayer so that you can decentralize the sequencer, so you can have a whitelisted established relationship with other operators. If an operator only trusts another operator in the cloud to run a ZKP for some operation, like an AVS, or even a light client that's going to require some sort of, hey, I need you to prove the execution before you actually even like download or view my state, you're going to need to verify my circuit first. So ZKM is it's not a token, it's not like a custom program. It's a general framework for writing zero-knowledge proofs. It was faster than RISC-0 when we were battle testing it, and we also found that it had a pretty conservative cost. We also found that it supported Go and Rust. We found that there was no token to prove, which is really important, and we got all the good cookies out of the box: Starks, Plunks, Groths, and this is the architecture that what I've learned over the last couple of weeks. Going through it, this is actually a slide that I took from Pavel because I think this perfectly explains the relationship of how a program is executed. You have program execution, you have a separate proof generation process, and therefore you can generate a proof and verify. Okay, thank you. So I hope this is interesting because this is a different way of excuse me. This is a different way of enabling proof generation for programs. Now, you're not generating an input variable. I built on Alio for a bit, so I actually can relate with some of the people in the room here. So on Alio, you actually create a program circuit in an instruction set. You post the program ID as a record, as a transactions hash on the prover network. And in this case, what you're going to do in Alio, you're going to submit inputs to that program. And in here, you're actually generating a proof of the inputs ahead of time, and then you can always verify and validate with that signature proof at a later date. But the inputs can be anything. It means that we can add a zero-knowledge proof of the GOAT node, right? The entire Geth EVM. And it takes a lot of constraints. It takes hours, like 35 hours to compile this. But at the end of the day, it is just code. It just works. Now, the perfect system that we were like, all right, this is going to be GOAT, right? This is it. It's something where we have GOAT holders. Somewhere the users are like, all right, there's some ecosystem. I get that I gotta pay gas, but I understand that there's some like yield sharing opportunity. What does that mean? So it's like, I understand that I got this thing called YBTC. If I hold this asset, then it's a yield. If I'm gonna be able to issue it, it's gonna be to a decentralized sequencer that is then making commitments and then verifying those commitments to and from Bitcoin. Now, owners should be able to lock their Bitcoin on layer 1, as well as locking the Bitcoin again on the layer 2 for the reason of generating a yield. That's how you generate a yield. You generate network transactions, and then you're able to lock the GOAT BTC inside of a sequencer, but the thing is that the Bitcoin is actually still on the layer 1. The layer 1 only made a zero-knowledge proof of what asset to mint on the layer 2. As what Pavel was explaining before, is that it's very similar to a mint and burn process. You have something that can verify the deposit address on Bitcoin space, and you can mint the same asset if and only if the taproot signature on Bitcoin matches the one that we prove here in L2. So how do we do that? First, you need to provide, we need to build all these various level components. So we need to build first the trustless bridge protocol, which is opt in BitVM2. This is going to take another about, I would say, a year in production, and there's challenges because it's very hard to verify through taproot. There's not enough tools. We need optimistic challenging, which effectively means we do what's known as a, hey, you commit proofs to the network, I need to be able to challenge you within 2 weeks so that I can later redact your proof. If you do a double sign and you're the validator, you're making a commitment as one of the decentralized sequencers. Who's to say that you're not lying about the transactions that you're making a commitment about? So that's why we have to create a challenge protocol so that anybody can actually challenge the validator, just like with any other consensus network. Now, the decentralized sequencer is the whole key of this. We're taking a lot of the technology stack from Meta since they've already implemented a decentralized sequencer for layer 2 on Ethereum. The cost efficiency of a rollup is the key that we're trying to achieve. This is technically the stack. So this vision here is this computation here, or these components here. So we did use this in-house ZKVM in order so that we can do a low-cost generative ZKP so that we can make commitments to and from Bitcoin. Now, the roll-up economic model, we also wrote a beige paper on how exactly to do the data optimization. You can look on our website, on our yield economic white paper. We have both a white paper and an economic white paper, in case if anyone wants to understand how that works. But we decentralized the sequencer, which is effectively the consensus of the layer 2. Now, layer 2 doesn't usually have consensus. We've enabled consensus, but directly to Bitcoin. So the data syncs with PTCL1, that is through BitVM2. This is how we can actually write a verifier script to BitVM2. It means that we take the rollup space, or a proof of thereof, of a rollup, and then we commit it directly to the BitVM2 script. And that actually writes a verifier that is compact enough to Taproot, to remove it thinking. So the compact proof that is in the zero-knowledge proof, but in Taproot, is roughly 64 bytes. And so you can actually verify this doing a rollback signature. If the proof is in the DA layer as the layer 2, you can always recompute the proof. And if you can challenge the proof, you can always tell the challenger, reveal your proof, and then they're going to reveal the proof. What they're going to do is that they're going to get a data sync with the data layer 1 and layer 2. They're going to reconstruct that hash. But we don't want to do that. We don't want to try to reconstruct proofs here. That's the purpose of doing a commit and verify. But if somebody challenges it, it's always there. That's the purpose of a consensus on L2. You know how hard that is to build? Okay. This is the hardest thing in the world to build type of shit. So it's an entangled rollup. Really. It's really that. So you have Bitcoin that is the verifier. It's basically your commitment layer. And Bitcoin can act as a universal verifier across any kind of machine. Bitcoin is a universal verifier. It's a Turing-complete machine. And so you can make operators that are specialized zero-knowledge provers that can actually write and verify validity proofs with Bitcoin. And we have to go a step further with decentralizing the sequencer set, where then we can add full node operational support, and that's where we can start getting to really interesting grounds like ABS or ZK Litecoin support for Bitcoin layer 2s. Now, since we enabled the ZKM, all the liquidity is actually native, and it's real. And so if we do enable the virtual machine for each of these sequencers, say the FVM, SVM, or whatever, the yield is really just the same. So all the Bitcoin yield, we get to optimize yield on Bitcoin, but we actually get to decentralize the liquidity without fractionalizing it across any of the layer 2s that we have a decentralized sequencer operating on Bitcoin for, which can be Ethereum, Avalanche, SVM, Son, Ton, you name it. This is the stack. And this is the hackathon. If you want to hack with us, please, this weekend's going to be really awesome. We're making a lot of front ends. If you want to just do some shit with us, I'm going to have a lot of fun. $5,000. If you want to learn about Go, if you want to make some smart contracts, if you want to do some AI, happy to reach out. Thank you so much, guys. I appreciate it. Do you have any questions?
Can I ask a question?
Sure.
What's the estimated size of your state?
Sorry, say that again.
So what's the estimation of your state size? Because you're verifying in the history, so you have some megabytes of sample each way.
Yeah, so the validity proof that we're compiling. So it's from start to belongs and then to gross 16. So it's the size variant of gross 16, which is roughly 256 bytes of data. And then you have to run BitVM2, which is a free Python script, so it doesn't actually cost anything to run that. And, but then it's a data availability, so it's the cost of maintaining the node. And that's the cost. It's not the cost of the proof generating or the commitment, it's the cost of storing data. So that's why data availability is really like a problem for Ethereum. You need data availability. We're likely going to partner with Weave so we can solve this problem early. Any other questions? Cool, thanks. All right, guys.
Thanks,